Greetings. In today's video, we will be looking at the physical properties of simple harmonic oscillators. First, we will define the simple harmonic oscillators and then introduce some mathematical notation, which is more familiar to physicists than mathematicians. Then we will look at some examples of the simple harmonic oscillators, mostly in 1 and 2 dimensions. And finally, we will be looking at a special case of two-dimensional simple harmonic oscillators that includes coupled equations. First, let us define the simple harmonic oscillator. A harmonic oscillator is a system that, when displaced from its equilibrium position, experiences a restoring force which is proportional to the displacement of the equilibrium position. So basically, if we have some particle displaced by some distance x from its equilibrium position, then the force will act in the opposite direction and have some proportionality constant. The consequence of this is that the system will oscillate sinusoidally about the equilibrium position, and from this the velocity and acceleration should also undergo a sinusoidal oscillation, sorry. Now we will introduce some mathematical notation. Through the entirety of the series, for some variable q of t, the time derivative will be denoted by q dot of t, and the second derivative with respect to time will be denoted as q double dot of t. This is because we will have some equations that include a lot of time derivatives, and we don't want to write d squared q dt squared and dn q dt n. So this equation looks quite clumsy. So we will just use the simplified notation. Now we will introduce the first case of one-dimensional simple harmonic oscillators. The simplest case is the spring mass system. According to Hooke's law, for solids, the strain is proportional to the applied stress within the elastic limit of that solid, namely F equals minus kx. Using Newton's second law, one can write the equation as the following. From this, we know that this is a second-order linear differential equation, and we can apply the following ansatz. And an ansatz is a guess solution that fits the differential equation. We use this ansatz, the real part of a times e to the I omega t plus phi, where a is the amplitude, omega is the angular frequency, and phi is some phase angle. Plugging this into the second-order linear differential equation, we obtain a quadratic equation, and one can solve for the angular frequency, which is square root of k over m, and hence the general solution will be x of t equals the real part of a times e to the I square root of k over mt plus phi. However, we can go one step further. By imposing the following initial conditions, for example, if we let x at time equals 0 equals to some displacement x naught, and the velocity at time equals 0 to be 0, one finds that the particular solution is the following. One may not see the resemblance between these two equations, but given that the real part of e to the I omega t, because e to the ix is equivalent to cosine x plus I sine x, so hence the real part is just the cosine portion, as x naught is strictly a real number. Now we will look at another example of the one-dimensional harmonic oscillator. Namely, this is oscillation in a sphere with uniform density. So consider a point mass traveling through the center of a large sphere of uniform density ρ. Using Newton's universal law of gravitation, we find that the equation of motion is as follows. However, given that the point mass oscillates about the center, the direction is not so important. We'll only focus on the magnitude. The reason why it oscillates about the center is because on the outside of the sphere there is less material, and at the center of the sphere there is more material, and hence the force towards the center is much greater than the outside of the sphere. And as the point mass approaches the center, it will accelerate, sorry, and then when it leaves the center, it will decelerate, but once it leaves the other side of the sphere, it will accelerate towards the center again, so it will continuously oscillate about the center of the sphere. One may note that this equation does not actually resemble the simple harmonic motion equation. However, if we write m as a function of the radius, and we write it as the volume multiplied by the density, we find that the differential equation transforms into a form that is similar to that of the simple harmonic oscillator. And one finds, by solving this differential equation, the oscillation frequency is only dependent on the density of the object, and also the time period. And just like the spring mass system, by imposing some initial conditions, at time equals 0, the point mass is at the radius of the sphere, and at time equals 0, the velocity of the point mass is 0, then the particular solution is as follows. And this solution should typically be remembered because it's a very general solution for the one-dimensional simple harmonic oscillator. Now, we will look at the simplest case of the two-dimensional harmonic oscillator, namely the pendulum. Consider a rigid pendulum of mass m and length m moving in the xz plane. The rigid portion is important because if the pendulum was not rigid and it was able to sling around, this pendulum would actually sling and it would not maintain a simple harmonic motion. So this rod must be rigid, and typically we don't use the word string, we use the word rod, so we note that it's rigid. For convenience, we should actually write the equation of motion of the system in spherical coordinates, or polar coordinates, sorry, because this system has a lot of spherical symmetry. If we let r be the radial distance from the origin and theta be the angular displacement, we know that the tangential acceleration is just g sine theta, as we see that this is a right angle triangle, and the x direction acceleration should be mg sine theta, and the z direction acceleration should be mg cosine theta. And by writing the tangential acceleration in terms of the angular acceleration, theta double dot, we obtain the following equation of motion. But note that this is a non-linear differential equation and has no analytic solution. However, we are physicists and we're not really interested in getting a unique solution. So what we can do is assume that the oscillations are small. And from this one can take the first order term of the Taylor expansion of sine theta and get an approximate solution. By doing this, we find that the oscillation frequency is equivalent to the square root of the acceleration due to gravity over the length. And by imposing the initial conditions, at time equals 0, we have some initial angular displacement, and at time equals 0 that the angular velocity is also 0. The particular solution for the pendulum with small oscillation is the same as the one-dimensional simple harmonic oscillator. However, if we want to do a better job and look at large amplitudes, we have to do the following. By using the chain rule, we can write the equation above as the following. Actually, there should be a minus sign here, but that's my mistake. And by writing this equation in this form, we can actually divide both sides by this partial derivative and make it 0. And by rewriting this theta dot as partial theta partial t, we can actually obtain the time period. And we can do some and by using trigonometric identities, we can write it in this form. And by writing it this form, we actually we can actually perform another simplification by substitution. If we let sine of phi be equal to the sine of theta over 2 over the sine of theta not over 2, and we let sine squared theta over 2 be lambda, we can actually simplify the equation much further. And note that at phi equals pi over 2, theta equals theta naught. So this would serve as the upper bound when we change our variables from theta to phi. By changing the variables from theta to phi, we obtain the following equation, which is a much simpler equation. But even though this equation is much simpler, we still cannot do anything with it because it has a non-analytic solution, and it's actually an elliptical integral. So we can actually obtain a better approximation by Taylor expanding the denominator. By doing the following and performing the integral, one obtains this. I'm not actually going to go through how this integral is obtained, simply because I'm not interested in the mathematical properties and rather the physical properties. So now we can so we obtain this. Now we go one step further and Taylor expand lambda as the following. And finally, we obtain the time period as a function of the initial angular displacement. And note that we can actually write the frequency of oscillation, omega, as omega is equal to 2 pi over t. So the frequency of oscillation would simply be 1 plus theta naught over 16 plus some higher order term, all raised to the power of -1. The next case of two-dimensional harmonic oscillator is a little bit more difficult, but I believe is geometrically very beautiful. So similar to the one-dimensional case, the equation of motion in a 2D harmonic 2D spring mass system is r double dot is equal to minus k over m r. These vectors, the r vector is a vector of x and y. And writing the equation in terms of the horizontal and vertical components, we obtain the following two equations, which is exactly the same as the simple harmonic, which is exactly the same as the 1D simple harmonic oscillator, and obtains the same solution. However, we must note that the amplitude could be different and the phase angle could be different. But by writing the difference in the phase angle as delta, the equation can be written as the following. And from the compound angle formula, we can further, not really simplify, but write it in a different form. And we note that this cosine omega t minus phi1 is actually equivalent to x over a1. And this sine omega t minus phi1 is obtained by the trigonometric identity sine squared theta plus cosine squared theta is equal to 1. So we can write this sine omega t as the square root of 1 minus cosine omega t minus phi 1. So by rearranging this equation, we yield this. And given that cosine delta and sine squared delta are constants, we obtain an equation for the conic section. If we let delta equal to pi over 2 from the equation from the previous slide, we obtain an elliptical equation. And when we let a1 equal a2, we obtain a circular equation. Moreover, if we let delta equal to 0, pi, or 2 pi, we actually obtain a linear equation. And this is very cool because for the different values for the difference in phase angle, we can obtain different shapes when we plot them on a graph. And the different shapes are called Lisa-Joust curves. So this would be either 0, 2 pi, or pi. This would be for pi over 2, but the different amplitudes. This would be for some other angle, and these would be for some angle as well. And you can see that these actually produce very beautiful geometric shapes. And personally is one of my favorite phenomena in physics. And finally we will look at a special case of two-dimensional harmonic oscillators, which include coupled equations. In this example, we will look at charged particles in a magnetic field. Consider a particle with charge q in a constant magnetic field in the y direction, pointing in the y direction. So B vector equals B naught J hat. Hence, from this, we can write the magnetic force from the Lorentz force law. So we get F equals ma, which is equivalent to qv cross b. And since we can write the velocity vector as the following and the acceleration vector as the following, we can write the equation of motion like this. And separating the components individually, we note that there is something peculiar. The x acceleration is dependent on the z velocity, and the z acceleration is dependent on the x velocity. So these equations are actually coupled, but the y acceleration is 0. So let's solve the middle one first, since it's the easiest. We're solving for the y component. We obtain that the y displacement is a linear function of time. However, the x and z components are a little bit more complicated. To uncouple the equations, we have to take one more time derivative. And this may not seem intuitive, but note that this x triple dot yields a double dot in the z. And we can just plug this z double dot with the x dot in it back into this equation. See? And then from this, we obtain an equation that resembles the simple harmonic oscillator. If we write x dot as v sub x and z dot as v sub z, we obtain the following equation that is the same, exactly the same as a simple harmonic oscillator. And thus, the velocity component of, in the x and z direction must have the same form as a simple harmonic oscillator. However, note that this is just the velocity. To get the displacement, we have to integrate with respect to time. So by doing so, we obtain the two following equations. And in either case, they still persist a sinusoidal oscillation. However, note that we have more parameters to solve, such as the integration constants and the phase angle and the different amplitudes. But this can be solved by some initial conditions. Well, that marks the end of this lecture. Hopefully you learned something new about simple harmonic oscillators, and please subscribe for more videos. Thank you.